Okay, I think we're going to get started. This is welcome to the Runtimes track. I'm Ian Lewis. I'll be the host today. So the first up, we have the building a Kata Kubernetes-specific hypervisor. And we have, as speakers, we have Andreea Florescu, who is a software engineer at Amazon, who works on the Firecracker VM. And we have Samuel Ortiz, who works on at Intel on Kata and Rust-VMM, and contributes to a number of open source projects like Cryo or Creo, depending on how you pronounce it. So with that, I'm going to welcome them to the stage. Thank you.
Good morning, everyone. Thanks for joining this wonderful session. Today, Andreea and myself are going to talk about building a Kubernetes custom and specific hypervisor.
Well, Samuel, actually, we are not going to talk about that because I did some tiny modifications to the presentation and it's not working.
Oops.
Oopsie. Nope. Uh-oh.
Are we?
Sorry.
Can you hold that too?
Yeah?
Can you hold it?
Yeah. Yeah, there we go.
Does the clicker never work?
I don't know. Yeah.
Thank you. Sorry
Totally
about that.
ruined the surprise, but yeah, so today we are actually going to talk about building a Kubernetes-specific VMM and not a hypervisor. And to understand why I'm saying that, let's just look a bit at the typical Linux virtualization stack. So we have the Linux kernel, and inside the Linux kernel we have KVM. And KVM is essentially making the Linux kernel to behave like a hypervisor. But we are not going to talk about this today, Samuel. What we are going to talk about is actually a layer up. So we are going to talk about virtual machine monitors, or VMMs, which are going to be used for managing virtual machines. And with that, I will let Samuel to get back to his presentation about containers.
Thanks, Andreea, for the correction. I appreciate it. So, yeah, we're going to talk about VMMs. Can I call it hypervisor? No, I can't. Okay. We're going to talk about VMMs and containers. And, well, it's a Kubernetes conference. It's all about containers and workloads. And you may wonder, what's the relationship between containers and VMM, containers and hardware virtualization? And there's a strong relationship. If I can make the clicker work. So the reason why we're talking about VMM and hardware virtualization today is because we want to have and define hardware virtualization and VMMs and hypervisors in general as a container isolation layer, as yet another container isolation layer. So what I mean by container isolation layer, I'm going to just explain that quickly. Typically, when you run your container workload on the host, you obviously want to isolate, well, contain your workload and prevent it from reaching other workloads and reaching the whole resources. And to do that, you're going to add isolation layers, as many as you need, as many as you want. And you would typically add namespaces, C groups, seccomp rules to, well, isolate your container workload from the host. You don't want your workload to be able to call any and every syscalls. You want it to be restricted on how many resources it can use through C groups and so on. So those are all isolation layers, and what we're trying to do with hardware virtualization, VMM, and hypervisors, we just want to add yet another isolation layer to this story. So we want the VMM to be another isolation layer that you can add to your container workload, depending on the need for security and the level of security that you want to reach with your application. So this is very well aligned with the overall container security architecture and design, which is mostly about defense in depth. The way you build your security story, at least for your container workload, is by defining how many of those layers you want to add. You want to be able to say, I just want to be able to run my containers through namespaces and nothing else. Or you want to add as many as you want. And what we're doing is adding hardware virtualization as another isolation layer and effectively making containers as secure as virtual machines. Okay, so you may think that this talk is all about how we're going to do this, how we're going to add this and define this as an isolation layer. But in reality, this is already integrated. This already exists. You can already today run your Kubernetes cluster and use some VMM as an isolation layer. It's seamlessly integrated through the work that we've been doing with a few other people through Signode and the OCI runtime specification. And today you can specify a Kubernetes runtime class and have your container workloads running through the VMM depending on the runtime class that you define. Even through the OCI specification, the actual RunC specification, if you want, you can define which virtual machine you're going to use, which guest kernel you're going to use, which hypervisor you're going to use, and how you're going to configure it. So this is all integrated today in the specification that I'm enumerating here. No? Sorry about that.
Uh-oh. Yeah.
Thanks. And so there's one well-known implementation of those specifications on how you're going to add a VMM as an isolation layer, and that's Kata Containers. How many of you here have heard about Kata Containers? Yay, we made it. I should take a picture of this and send it to my management. It's been a long road. So yeah, Kata Container is kind of a canonical implementation of this work, and the Kata Container team has been working with the Kubernetes SIGs and working group to make that happen. And the way you do it today is by simply, quote unquote, simply adding a runtime class name to your pod definition. So by saying I want to run Kata QEMU as my runtime class, you're basically going to run your container workload inside a QEMU defined virtual machine. So your VMM is going to be QEMU, and your runtime is going to be Kata Container. You can do something similar, and instead of using a QEMU as a VMM, you can decide, okay, I'm going to use a Firecracker as a VMM. And this is, well, another runtime class. It's Kata FC. And Kata Container is going to be the runtime. Firecracker is going to be the VMM. It's as simple as it gets. Okay, so you may think that it's very simple. This diagram makes it look that it's very, very simple. But if you look at a little deeper into the architecture and how this is implemented, it's not that simple. The whole container ecosystem has a lot of assumption on the fact that the container workload is actually run on the host CPU, bare metal on the host. And so to make that happen, and the way it's implemented today is through an actual virtual machine. So when you use QEMU as your VMM or Firecracker as your VMM for Kata Containers, you're going to be running your workload and your pod inside a full-blown virtual machine. So your pod is going to run on top of a real Linux kernel, an entire dedicated Linux kernel to your pod. There's going to be a Kata agent running on the virtual machine to basically handle, multiplex, and manage all the commands that you get from your runtime into your workload. So even the picture on the right is still a simplified description of what it takes to actually make that happen. So we've been talking about VMMs, Kata Containers VMMs. And as of today, with Kata Containers, you can run your workloads through different VMMs. As I said, depending on the runtime class that you select, you're going to have different VMMs running your workload. And we support 3 different VMMs. We support QEMU, we support NEMU, which is the stripped-down version of QEMU, and we also support Firecracker.
Whoop! Firecracker!
Firecracker maintainer, she can help. Okay, so the default VMM for Kata Containers is QEMU. QEMU is a high-performance VMM. It's very stable. It's also very versatile, so it supports all sort of architecture. It supports all sort of platforms. It emulates hundreds of devices. So it basically does everything and anything you can think about when basically building a virtual machine. The cost for this is that the QEMU code base is large. It's more than 1.5 million lines of code. And its footprint is also relatively large. So you get the performance and the versatility, and the cost for this is obviously more lines of code and a larger footprint. On the other side of the VMM spectrum, there's Firecracker. Firecracker is much smaller than QEMU, but it also has a much narrower focus on one specific use case, which is serverless. It's designed for supporting serverless. It's running AWS Lambda. I don't want to run your, but anyway, yeah, it's running AWS Lambda. It's very small, so we're talking about 20, 30 1,000 lines of code, not lines, but 1,000 lines of code. And well, it's very small, and as a consequence, the scope of Firecracker is also smaller than QEMU. It's so small that it cannot support all container workloads. So if your container workloads needs to mount a volume, which is fairly typical with Kubernetes, you're not going to be able to do that because Firecracker doesn't support share file system from the host. If your workloads needs to assign your host GPU into your container, you won't be able to do that with Firecracker. Firecracker does not support direct device assignment. So there's a few things in a container definition that Firecracker does not support. But if you want to do serverless like a workload, then it's definitely the right approach. So I think we have like this big elephant in the room when we're saying we're adding hardware virtualization as yet another isolation layer. Obviously, for security reasons, we want to make containers as secure as VMs. But on the other hand, we're adding this new software component here, a VMM, that can be large or very large, like QEMU, that can be very small but limited. But basically, on one hand, we're saying we want to improve security and the security story of containers in Kubernetes. And then on the other hand, we're adding a software component that's, can extend the attack surface of your container workload. So what we believe is that there is a need for defining a VMM that supports all container workloads, but only container workloads. Nothing less, nothing more. Not QEMU that supports basically everything, and something larger than Firecracker to support all container workloads. So this is mostly what we want to talk about today, finally. So before going into more details about this, we need to understand what it means for VMM to support all container workloads. And we need to understand what a container runtime needs to do. And to do that, we're going to look at specific container runtime specifications. We could look at the OCI one, which is a low-level specification for container runtime. But instead, we're going to focus on the Kubernetes CRI specification. As a matter of fact, the CRI implementation, for most of them, end up calling an OCI runtime eventually. So it makes sense to look at only the CRI stuff. So what we're going to do now is look at the CRI specification and try to map that to actual hardware virtualization requirements and technology to understand what we need to implement in a VMM, in a Kubernetes-specific VMM. Okay, so if you look at the CRI specification, there are a few interesting things. One of them, the very first one, obviously, is that you're going to need to send commands into your container workload. You're going to be able to interact with your container workload inside the virtual machine. It seems very obvious. It seems like a natural thing to do, but it's actually not. You don't want to run an SSH server inside your virtual machine to do that. Instead, you want to be able to open like a gRPC socket directly into your virtual machine. And so to do that, you're gonna need a implementation, a virtual socket kind of implementation. You're obviously gonna need a container image. Your container workload is gonna run inside your virtual machine. And to do that, you're gonna have to mount the container image from your overlay implementation on the host inside the virtual machine. That's something you obviously do when you're running on bare metal. You just mount or run your container directly from the host. When you're running it inside a virtual machine, it's much more difficult. And to do that, you're going to need virtual storage, obviously. An obvious requirement is networking. CRI specifies that you may need a networking endpoint with your container. That's fairly typical. So you're going to need virtual networking as well. There are a few other interesting requirements, like the device structure inside the CRI specification. that says, well, you might want to actually mount a device into your container workload. You're gonna want to mount your GPU to do ML type of workloads inside your container workloads. That's very easy to do with a bare metal container. You just basically mount or bi-mount your /dev entries into your container workloads. With a virtual machine, it's a lot more difficult. You need to directly assign an entire device into your virtual machine. This involves IOMMU, VFIO, and so on. So what you're gonna need is direct device assignment. The mount structure, you want to be able to mount volumes and share secrets with your container workloads. Again, very easy to do with a regular container. With a virtual machine, that means you're going to have to implement a whole shared file system para-virtualized implementation for your container workload. So you want your virtual machine to be able to share a very tiny part of your file system and mount it inside your virtual machine. And finally, the CRI spec says that you have to be able to update your container resources. Maybe your container is going to need more CPUs or less CPUs or more memory. And to do that, well, again, very easy on bare metal containers. With virtual machine, you're going to have to hot plug things into the virtual machine. Adding a CPU means you need to make your virtual machine aware that a new CPU is showing up. More memory is the same thing. Removing memory is very difficult. So you're going to need resource hot plugging. How does that translate into actual virtual machine and hardware virtualization software technologies? For the virtual socket storage and networking, well, essentially you're going to need para-virtualized implementations. The typical way to do this in Linux is VirtIO, or maybe vhost user, which is a user space implementation, well, not user space, but a deferred implementation of VirtIO, where you have separate device emulation. For direct device assignment, we're going to need a VFIO implementation. So VFIO is the kernel API for handling IOMMU-based devices. So you're going to be able to talk to your device through IOMMU and from user space, and take that device and assign it to your virtual machine, so that your virtual machine, as a process, is going to see directly this device and use it directly, almost as fast as bare metal usage. The shared file system requirements translate into, again, a para-virtualized implementation. Right now we support 9PFS. We're going to deprecate that for VirtIOFS, which is a new implementation. And finally, resource hot plugging. There are many ways to do hot plug into a virtual machine. You want to do memory, CPU, NVDIMM hot plug, and other things. And one way to do that is to go full ACPI. So you can use ACPI to do hot plug, or you can use PCI to do device hot plug, but you won't be able to do a CPU hot plug with PCI, for example. So when you go full ACPI, you can do an entire hot plug support for your virtual machine. And well, as you probably guess, implementing a full ACPI in your VMM is not a small thing. So compare those requirements to your bare metal containers requirements. When you do a bi-mount in with your bare metal containers, you're gonna have to do an entire shell file system or an entire VFIO implementation for your virtual machines, and so on. So if there are people in the room that are working on CRI specification and runtime specification, please look at this and understand how difficult it is for anything that you add to the specification to support that through hardware virtualization. Okay, so we now have a small set of requirements for our VMM. And if you look at QEMU, for example, it supports all of this. If you look at Firecracker, it supports some of this, not all of it. And what we want to do is build a VMM, a virtualization stack that only supports this and nothing else. So where could we get those components? I think Andreea wants to talk about this.
Yeah, it's a super exciting process. So, yeah, so all these components, you can get them from Rust-VMM. And Rust-VMM is a new open source project that is providing virtualization components, building blocks for building your own virtual machine monitors or hypervisors, if that's your thing. And to understand better, let's look a bit at why we decided to start this project. Oh, and by the way, the virtualization components are crates, which is Rust packages. So the whole project is Rust. Now, so let's see why we decided to start Rust-VMM. And the first reason is actually to reduce code duplication. There are already 2 virtual machine monitors that are written in Rust, One of them is CrossVM, which is providing isolation for application in Chrome OS. And then we have Firecracker, which provides isolation for multi-tenant workloads in the cloud. So that will be AWS Lambda and AWS Fargate today. But that is not the only reason, and that is not a reason that might be interesting for everybody here. But when we are sharing these components, because they are both written in Rust and they are similar in some ways, we also have to provide a clean interface in order for them to be, so for these components to be easily used by multiple projects. And then we also want to focus on security and testability, and we want to provide a high standard for these components, mostly because they are going to not be only used by one project, but they are going to be used by multiple projects. So you want to make sure that they are well tested and they work for every use case out there. Now, with these separate components that we are having, it gives us a benefit, and that benefit is that it's much easier to do security testing in terms of fuzzing. So you now have this component that has a clean interface that you can call into, and it's much easier to provide fuzzing for it. And having these components separate and pluggable and like a Lego also gives this new benefit, which is you can develop VMMs faster than before. You don't have to re-implement everything again. You don't have to work on KVM wrappers. You don't have to work on Vert.io and so on, because these components already exist, which means that essentially you can focus on your on the key features of your product instead of re-implementing everything from scratch. And now that we talked a bit about why we decided to start Rust-VMM, let's also look a bit at the Rust-VMM development process. And I want to start with the people that are already contributing to Rust-VMM. There are a few companies that are already working on this. We also have individual contributors that are reviewing the code and asking questions, submitting ideas, and so on. And when we are talking about adding these components to Rust-VMM, we are currently having two processes. So one of them is to add components that already exist in either Firecracker or CrossVM. And some examples here are like KVM wrappers, the Vert.io implementation, abstraction for a guest memory, and so on. Then we are also adding components from scratch. And these are some components that are interesting for the container VMM. And some of them are like vhost and ACPI, which are components that Samuel talked about before. Okay, so now let's take an example of a crate that already exists in both Firecracker and CrossVM, and just try to understand a bit what's happening there. So we have the VM memory, and the basic component of the VM memory is an abstraction of guest address. And in Firecracker, the guest address is represented as a usize. Now, we want to make something useful with this guest address, so we want to create memory region. And the memory region is basically an abstraction that uses a guest address, which is the start of the memory, of the guest memory, and then it also has a chunk of memory, an anonymous shared memory, and essentially those two represent a memory region. Now, to actually have a guest memory, you will have a list of multiple non-overlapping memory regions. But this is very specific to how Firecracker works. And now we want this crate to be used by multiple projects. So what do? We are converting everything to a trait. And a trait is essentially an interface in Rust. So instead of having the guest address as a usize, you are having a trait of guest address, which can be implemented with usize, with U64, and so on. We are also having memory regions as a trait and the guest memory as a trait. And one of the things that you might notice is that we don't only support anonymous shared memory anymore, but we also support memory backed by file. And this is quite interesting because it allows us to support many other use cases, like, for example, vhost user. Now, everybody can submit ideas about crates that they think that they're useful for Rust-VMM or for other projects, and we have a process around it. So the first thing that you have to do is to open an issue in our community repository. And in that issue, you have to pitch your idea. You have to talk about how is it going to be used, who is going to use it, what are the dependencies, what is the design, and so on. And after discussions about design and naming, which is very hard for us, we actually create an empty repository or an empty crate. And against this empty crate, we are submitting pull requests based on the design discussions in order to obtain crate in development or a useful crate, a crate that has functionality. But now, as I said, these crates are going to be used by multiple projects. So obviously, there is a list of requirements that you have to have before we are publishing the crates on Crates.io. Do people know what Crates.io is? Can you raise your hand if you know what Crates? Okay, so Crates.io is basically the main, I always forget the word, is the main
Repo?
Yeah, it's sort of a repo for packages, for Rust packages. So it's basically the place where you get the packages from. So now let's get back to it. So from a crate in development, there are a few things that you have to do in order to obtain a production-ready crate. So a crate that is going to be used by products like Firecracker. And we really want to emphasize the importance of testing. So we have continuous integration, and all the crates must have continuous integration and tests, and make sure that the quality standard is very high. Then we are also requiring a license, and we are having some discussions now to have a dual license, which will be Apache 2.0 and BSD Clause 3. Then another important thing is documentation, probably one of the things that I find the most important, especially in a place where you are going to use these components so in a place where these components are going to be used by multiple projects, multiple people that might not have worked on them specifically. So we really want to have documentation that contains like high-level design, how is the public interface going to be used, and so on. And then we reached the file, after we did all these things, we reached the milestone 2, which is publishing the crate on Crates.io to make it available to everybody. Now, the current status of crates in Rust-VMM, we have some crates that are still in development. So if you go on the GitHub project, you will see that there are some crates that seem like nothing is happening there. They're empty repositories. That's because we are still designing them. We are still working on the design. We are still trying to merge pull requests and so on. Then we have a crate that is in development, which is the VM memory that I discussed earlier. And we currently have only 2 crates that are actually published on Crates.io and are used in production. These ones are the KVM bindings and the KVM IOCTLs, which provide some primitives or an interface to interact with KVM, with the KVM API. So now let's take an example of how Rust-VMM is going to actually work in practice. And because most of the crates are still in development, we are going to take a paper example. So first, we are going to start with our VMM API, which is basically the bridge between the VMM, the virtual machine, and the client that is going to use it. And after defining the VMM API, we can take a look at the components that currently exist in Rust-VMM. And the thing is that we don't have to take everything, because these are separate repositories, separate components. So the first thing, in order to create a containers VMM, is that we are going to select the components that Samuel talked about earlier, which are specific, sort of, to the container use case. But these components by themselves, they can't work. So you can't have a VMM only with these components. So you need some other things as well. And so we are going to get the KVM wrappers. We also will need a minimal kernel loader that is going to load our kernel image into the guest memory. And we are also needing the abstraction for the guest memory. Now, the only thing that you have to do after all these components are available is to write the glue code. And essentially, the glue code, what it does is it creates the interaction between all these components, and it also interacts with the API in order for users to be able to configure the virtual machine. Now, when we are looking at the serverless example, things are a bit changed. And we don't need, so if we take the Firecracker example, we don't need ACPI, we don't need BERT-IFS, so we are just not going to take them. So, but we do need some other things. So one of the most important thing in a multi-tenant environment is also the ability to limit resources. So limit the block, limit the network, and so on. And we are limiting these in terms of operations per second and bandwidth. And this whole functionality is offered in the rate limiter crate, which we are going to add to our VMM. And then we are also adding CPU ID, which is a crate that provides a mean for specifying templates for your virtual machine. So basically, you're making your virtual machine look like something else. And that is because you want to provide the same experience across multiple platforms. But the other things are sort of the same. So you will have a different API, but you're still going to have to write some VMM glue code and use basically most of the components out there. So now that we gave this example, let's look a bit in the future. Let's see what is next for Rust-VMM. We obviously have to add all those components that I'm talking about. But what we are also trying to do right now is to provide hypervisor agnostic crates, because there is an interest for people to not only use KVM as a hypervisor, but others as well. So one example is Hyper-V, so we are trying to work towards that as well. Now, we are also using these components. We are trying to move these components into virtual machines that are already out there. One of them is Firecracker, and in Firecracker, we are already using all the components that are published on Crates.io. And obviously, we are trying to create new specialized virtual machine monitors, and one of them that was recently announced was Cloud Hypervisor, by Intel. And in the future, we might as well see a container VMM. But the future is set in stone. So if you have ideas, or if you think that we are going in the right direction or in the wrong direction, or if you have any suggestions, you can come and decide with us, like what the future of Rust-VMM is going to be. And you can be part of Rust-VMM by subscribing to our email list. We have discussions there. And you can also submit, if you have an idea about a crate that is going to be useful, you can submit an issue request, review request, and people will look at your issue and we will provide feedback.
Okay, thanks. Very quickly, as a conclusion, we have 1 minute left. So what we want to say here is that there is a need for a container and maybe Kubernetes-specific VMM. We think that Rust-VMM is the right solution for this. There's already some VMM that are being implemented by using Rust-VMM that go into this kind of direction. And yeah, we really think that Rust-VMM is going to provide the building blocks for all of this. So very quickly, we have our GitHub, obviously, Rust-VMM, surprisingly. So go there. There's a community repo where you can submit issue, where you can follow basically what the community is doing around that project, which crates we're working on, which technology we're adding to this. Just go there and chime in. And we have, because we're super hype, we have a Slack channel. No IRC, sorry about that. But yeah, there's a Slack channel and you can join and ask questions or tell us what you think about it. Thank you very much.
Thank you.